Want to learn engineering and science? Well, you've tuned in to the right channel. Hit subscribe and press the bell icon and never miss an update from us. Hi there guys, how are we doing? This is your friend and tutor Manas, and today let's continue with our discussion on SF and BM diagrams. Okay, now the method that we're going to be discussing again is the method of sections. So let's take up a problem based on this method. Here we go. Draw the SF and BM diagram for the beam loaded. Also locate point of contraflexure. Now this point or point of contraflexure is something that can only be located, can only be situated after we have the bending moment diagram. Okay, so before that, let us go ahead and analyze this beam. Okay, so the first thing that we have to do immediately is that we need to find the reaction at supports. Let's say the reaction at B be represented by RB and the reaction at C be represented by RC. And you can clearly see that the external loads are vertical in nature. One is a point load while the other one is some sort of a UDL, and both of them are vertical in nature, and therefore the reactions will also be of the vertical nature. Okay, so let's go ahead and let's apply what we've learned in mechanics so far. Summation of f of y is equal to 0, RC plus RB minus AT. Okay, RC plus RB minus 80. Now guys, watch out, this is 30 kilonewton in 1 meter, 30 kilonewton per meter, which means in 1 meter portion of the beam the total load acting is 30 kilonewtons. Therefore along this portion of the beam, that is from A to C, we have a distance of 2 meters. The total load acting will be just double, 60 kilonewtons. Okay, so it will be acting downwards. Minus 60 is equal to 0, and I can rewrite this in equation in a better way. RC plus RB will be equal to 140 kilonewtons. Okay, now let us go ahead and let us apply this moment equation, and we are going to take moment about this point C. So let us go ahead and do that. So we've got this RB multiplied by this distance, that is 3 plus 2, 5. So 5 times of RB, and RB is in fact producing an anti-clockwise moment and hence a positive sign. This AT is producing a clockwise moment and hence a negative sign. Okay, a clockwise moment at C, you can say, and this essentially has to be multiplied with this CD, which is equal to 3. Okay, what else is there? So we have to work with this 30 kilonewton per meter force also. Now if we were to replace this uniformly distributed load with a point load, you can do this. Okay, that's it. So that's the point load which is going to replace the uniformly distributed load, and whose magnitude will be equal to 60 kilonewtons. So for 1 meter it is 30, so for 2 meters it's going to be obviously equal to 60, which is going to act this distance from point C, and this distance is how much? Half of this AC portion, that is simply 1 meter. So 60 multiplied by 1, anti-clockwise moment, 60 multiplied by 1, and all of this stuff is going to be equal to 0, and you just need to solve this equation so that you can have the value of RB, which is going to work out as 36 kilonewtons. You just need to put this value 36 over here so that we can have the value of RC, which is going to work out as 104 kilonewtons. That's it. Now let's go ahead and let's take the section between D and B. Let me write this. Okay, so let's have the section. Here we go, and we are going to consider the portion of the beam which is towards the right of this section. Here it is, and since this section has been done from the right, let's say the section is at a distance of X, and here we're going to have this force 36 kilonewtons, and obviously you know the sign convention, shear force upwards and bending moment clockwise. Anything else? No, that's it. Now let's go ahead and apply the equations of equilibrium. Summation of all the forces in y direction is equal to 0. Vx and 36, both of them upwards. So let me write this: Vx plus 36 is equal to 0. Hence you can rewrite this: Vx is equal to what? Minus of 36 kilonewtons. So essentially we can conclude that between point D and B, the value of shear force is independent of X. Doesn't matter what the value of X is, that is from 0 to 2, the value of shear force will remain unchanged. Okay, so you can write this at X is equal to what? 0. If we squeeze this X, we are going to find the shear force at B. The value of shear force is going to be equal to minus 36 kN, and again at x is equal to what, 2 meters, we're going to find the value of shear force at point D, which again will be equal to negative of 36 kilonewton. Okay, now let's go ahead and let's apply the moment equation. We're going to take the moment about, let's say, this point, okay, is equal to 0. So we have mx, again, since it's clockwise, negative sign, we've got this 36 multiplied by x, producing an anti-clockwise moment, hence a positive sign, plus 36x is equal to 0. I can rewrite this, mx is equal to 36x. So what you need to do in order to find the moment at B, let's put the value of x is equal to 0. So at x is equal to 0, the value of bending moment at B will be equal to 0, and at x is equal to 2, we will be getting the value of bending moment over here, that is at point D. Okay, you just need to put this value, 36 into 2 is obviously 72 kNm. Well, that's it. So we have worked out the shear force and bending moment values between section D and B. Now let's go ahead and let's do the sectioning between C and D. Let me write this, section between C and D. Okay, so let's have the section line and let's consider the portion of the beam which is towards the right of this section. Here we go, and obviously we have taken the section from the right. The shear force will be upwards, bending moment clockwise, and let's say the distance of this section from the right hand support, let's say, be represented by simply x. Alright, now the next thing to do is to immediately apply equations of equilibrium. Okay, so let me go ahead and do that. We have this summation of all the forces in y direction is equal to 0, Vx, and over here, that is at point B, there is going to be a reaction whose magnitude is 36 kN. So Vx plus 36, what else, minus 80, since 80 is downwards, minus 80, anything else, no, all of this stuff is going to be equal to 0. So Vx works out as positive 44 kilonewtons. So again, the shear force value between C and D is independent of x. So it doesn't matter what the value of x is, from 2 to 5, the value of shear force is going to remain same, that is 44 kilonewtons. So essentially at x is equal to 2, shear force at D will be equal to simply 44 kN, and at x is equal to 5, shear force at C will be equal to again positive 44 kN. Now we'll go ahead and we'll try to find the bending moments at D and C. Okay, so let me apply the bending moment equation about this point is equal to 0. Okay, so we have got this mx clockwise, hence negative minus of mx, what else, 36 multiplied by this distance, that is x, again producing an anti-clockwise moment, and hence positive 36x. We've got this 80 multiplied by this distance, so that's the perpendicular distance for this 80 kilonewton force. This is x, this is 2, so the remaining distance is how much? This is x minus 2. Pretty simple. So producing a clockwise moment, hence a negative sign, minus 80 times of x minus 2 is equal to 0. So that's it. Let me reframe this in a better way. We have mx is equal to 36x minus 80 times of x minus 2. So when you put the value of x is equal to 2, you'll find the moment at t. Okay, so at x is equal to 2, we're going to find the moment at where t, which is going to be equal to 2 minus 2 is 0, 36 into 2 is 72. Let me write this, 72 kNm, and at x is equal to 5, we'll have the moment at C, whose value is equal to negative 60 kilonewton meter. So the bending moment values have been worked out between C and D. Now let's go ahead and let's try to make a section between A and C. Let me first write this, section between A and C. Okay, so let's have the section line. Here we go, and let's consider the portion of the beam towards the right of this section. Here it is, and let's say this section line is at a distance of x from the right hand support. Okay, now so let me write the reactions over here. This is what, this is 36 kilonewtons, and how much is this reaction at C? Let me check, 104. Okay, so the magnitude is 104 kN. All right, now since the section from the right hand support has been taken, okay, the shear force will be considered positive and the bending moment as clockwise in nature. Okay, so the first thing to do, summation of all the forces in y direction is equal to 0. So we have this Vx, we have this 36, we have this 104, all of them upwards, therefore positive. Vx plus 36 plus 104 minus 80, since this is downwards, minus 80. Okay, but what about this UDL? Now this UDL is having a magnitude of 30 kilonewton per meter. Okay, and if you were to replace this UDL, okay, by a single concentrated load or a single point load, okay, how can that be done? Watch carefully. Now this portion is something that we need to focus on. Okay, that is the portion of the beam in which the UDL is acting right now. All right, how much is this? This is X. How much is this from here to here? This is 5. So obviously this distance is X minus 5. All right, so the UDL can be converted into some sort of point load, and you can say, since in 1 meter the total load acting is 30 kilonewton, therefore for a distance of X minus 5, the total load acting in the downward direction will be equal to 30 times of X minus 5. Okay, fine. So that's it, minus again 30 times of X minus 5, and all of this is going to be equal to 0. Now we need to frame this in a better way. We can write this as Vx is equal to 30 times X minus 5 minus 60. All right, now we need to put the value of X is equal to 5 so that we can get the value of SF, that is shear force at C. So at X is equal to 5, we have shear force at C, which is going to be equal to 5 minus 5 is 0. And again, this whole term will be 0, 0 minus 60 is minus 60. Minus 60 kilonewtons. Okay. And at X is equal to 7, we are going to get the value of shear force over here. That is at point A. Alright. So you can do this calculation and you're going to ultimately get the value of shear force at A is equal to 0. A big 0, man. Now let's go ahead and let's try to frame the moment equation. Let's say about this point is equal to 0. Okay, so the first thing to do is this clockwise moment mx, negative of mx, 36 multiplied by this distance, that is x, producing an anti-clockwise moment, plus 36x. What else? 80 times of this much. So what is the distance that we need to deal with? Okay, so this essentially is the distance, perpendicular distance for this 80 kilonewton force. How much is this? This is going to be equal to x minus 2. Just think about this. This much from here to here, this is x, and this is how much from here to here, it's 2. So this distance is going to be equal to x minus 2. So 80 times of x minus 2 producing a clockwise moment, negative sign, 80 times of x minus 2. Okay, what else? We have to deal with this UDL also. So the UDL has been converted into some sort of point load. Okay, this point load is 30 times of x minus 5, and if you're taking more about this point, it is going to produce a clockwise moment, hence a negative sign. Magnitude of this converted UDL in this sort of a point load is 30 times of x minus 5. This has to be multiplied with a perpendicular distance, and if you watch carefully, this is that perpendicular distance. Okay, this much amount is x minus 5, so half of x minus 5, x minus 5 over 2. Okay, so the force is 30 times of x minus 5, and this is the perpendicular distance, x minus 5 over 2. So let me just write this, x minus 5 over 2 is equal to 0. Now, okay, the moment has arrived to frame this equation in a better way. Mx is going to be equal to 36x minus 80 times of x minus 2 minus 30 over 2 is obviously it's 15, and it's going to be equal to x minus 5 square. And what you need to do is you need to put the value of x is equal to 5 so that you can get the value of moment at C, which is going to work out as negative of 60 kNm. And when you put the value of x is equal to 7, you're going to get the value of moment at point A, which is going to be equal to 0 k n m. That's it. So at the free end, essentially the value of bending moment will be equal to 0. Okay, so that was all about the computing the values of shear forces and bending moments. Now let me go ahead and highlight all the values. Okay, now the time has arrived to construct the SF and BM diagram. So let me have vertical lines from all these 4 points. Here we go. Let me have the baselines. So this baseline represents a 0 shear force, above which we'll have the positive values of shear forces, and below which we'll have the negative values. Okay, the same thing is with the bending moment diagram also. This is the 0 bending moment or 0 kilonewton meter bending moment, above which we'll have the positive values of bending moment, and below which we'll have the negative values. So let's start by locating the shear force at B. Okay, so at B we have minus 36 below. Okay, at D again minus 36 below, and at D again we have plus 44 here, and then at C we have plus 44 here, and at C we have shear force as minus 60 somewhere here, and then finally at point A the value of shear force is 0. That's it. And when you join all these points, this is something which is going to happen. We are going to start from here. Okay, line, 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 line again, and you can clearly see that here shear force was independent of X. Okay, here also shear force was independent of X. Let me show you where. Here also. Okay, that is why a constant line, and then from 44 to 60, and then finally from 0 to 60. From 0 to 60 you can clearly see the value of shear force. This shear force is sort of an equation of a line, and therefore this is how you need to plot it. All right, lot of stuff. Finally, let us do the bending moment plot. Starting from bending moment at P, we have the 0 value. Okay, what else? A bending moment at T 72 over here, that is at T. Okay, then we have bending moment at C minus 60 somewhere here, minus 60 below baseline, and then finally the bending moment at A, obviously going to be equal to 0. Now the bending moment equation between section D and B is that of a line, and therefore these 2 points will be joined with the help of a simple inclined line. And then between D and C, between T and C, again this equation is that of a line, therefore we have this line. And finally between A and C, this equation is sort of a polynomial of 2 degree or a quadratic equation, and hence the quadratic equation essentially represents a parabola. So what we're going to do, all the points in between A and C, when they are joined, they form something of this sort, that is a parabola. Let me write it over here. Now guys, you can clearly see the bending moment over here was positive and the bending moment over here was negative, and this is exactly the point where the bending moment has changed its sign. Okay, this is positive and hence represents sagging, and this is negative and hence represents hogging. What essentially I'm trying to say, if you try to make a point, if you try to just do this, let me join this. Okay, something of this sort, and when the beam bends it would be something of this sort. This is where sagging happens, positive bending moment, and this is where hogging happens, a negative bending moment. All right, now if we were to find this point or the location of this point, let's say this distance is X. So this point has been obtained between C and D. So we have a moment equation for C and D. Okay, and between these 2 points the value of moment over here is 0. So between C and D we have this as the moment equation. Where is it? This one. Okay, and the point where the bending moment changes its sign, this point is essentially known as the point of contraflexure. Now in this part what we are going to do is we are going to find the location of point of contraflexure, and for that what we need to do is, since this point has been obtained between C and D, and therefore what we are going to do is we are going to put this equation, this mx is equal to 36x minus 80 times of x minus 2. Mx is equal to what? 36x minus 80 times of x minus 2. We are going to put this equal to 0, since the value of bending moment over here at this point is equal to 0, and correspondingly we will be getting the value of x. And if you just try to solve this equation, you can do that pretty easily. The value of x will be equal to 3.64 meters. Okay, so this is the value of x, which is equal to 3.64 meters. So that was the point of contraflexure where the bending moment changes its sign. So guys, that was a really long problem, and after watching the video I would strongly suggest all of you to make this construction in a copy, in a notebook. Go ahead and do that. Explore whatever you have learned till now. So that was all from my side for today. If you've got any doubt or query, do write them down in the comment section below. I'll be very happy to answer them. And if you believe that this video tutorial has added value to your knowledge of engineering mechanics, then do share and like this video, subscribe to this channel and press the bell icon so that whenever I upload a new video, you get a notification. Well, I'll be back with more videos on engineering mechanics and engineering drawing. Until then, it's a wrap. This is Manas Patnaik signing off. Take care, have a great day and keep learning.